Okay, so now that we've talked about the different kinds of foundational features in Java 8, right? So the functional interfaces, the lambda expressions, the method references. Let's take a look and see how these can be applied to writing a concurrent program. And this will also give us a chance to talk briefly about some of the foundational concurrency mechanisms that are part of Java. This example is available in my website. And as you'll see, what it's going to do is it's going to look through a bunch of plays by William Shakespeare, and it's going to look for certain phrases that occur in the plays. So you can use it to search, and it'll tell you where these phrases occur in which play. So I'll show you that example, and then I'll also discuss the pros and cons of this solution. And the reason for doing this is that's going to motivate what we'll cover next, which is the Java 8 streams framework. All right, so let's talk about some simple applications of Java 8 features in the context of concurrency. So we're going to use these features to start and join a group of threads to search for phrases in the works of William Shakespeare. Let me just give you a quick summary of what a thread is. The ironic part is that for the next foreseeable future, we're going to talk a lot about parallelism and concurrency in Java. And ironically, because we'll be using the Java 8 features, you won't actually have to know anything about Java threads, which seems kind of weird. But it does help to know a little bit about them because it helps to understand what's going on under the hood. Naturally, the parallel and concurrency frameworks we'll talk about use threads. They just don't expose them to you as something you have to program directly. But what a thread is basically a unit of computation, and it runs code in the background concurrently with other threads or the main thread, and it's able to execute these instruction streams that may be mapped to multiple cores so that things can truly run in parallel. Even if you only have one core, there may still be some advantages to using threading in terms of reducing the complexity of the program by improving the program structure, improving responsiveness, and so on and so forth, which we may talk about later in more detail. So this particular example we're going to look at is going to use Java 8 features to start a group of threads. And so what we're going to do is we're going to end up with a list of threads, and then we're going to iterate through it using the for each method that we've talked about. And we're going to say, hey, for each thread in this list of threads, start the thread. So we're going to pass in the thread : start method reference. And under the hood, what that'll do, of course, is that'll cause a thread to be spawned. And when a thread is spawned, it creates a stack of activation records which are used to handle the method calls that occur in that thread. And that stack of one thread is different from a stack of another thread. So the two can run in parallel, and they won't interfere unless you do something crazy with your code that causes race conditions or interference or so on, which we'll talk more about that too. So we're going to talk about how we can use thread start as a method reference to spawn a bunch of threads. And then we're also going to show how you can use for each, the Java 8 for each iterator method, in order to join threads. So thread join basically means if I have one or more threads running in the background, if I join a thread as another thread, I will wait for that thread to finish before I can continue. That's what's called a barrier synchronization. So those are two very simple thread operations. Yes?
If join waits for the other thread to finish before joining them, when would be exception?
Oh, great question. So the question here is, there are two parts to your question. Part number one is, if a thread is running, or if I have a reference to a thread and I say join on it, then I'll wait until that other thread is done. That thread might end up being interrupted. And if the thread is interrupted, then I will catch the interrupted exception. So if it doesn't finish gracefully, if it finishes because it was interrupted, then the interrupted exception will be joined. And that may be a different path through my handling code, or not. It might not be. But that's what you're seeing here is something called a checked exception. So Java has two kinds of exceptions. It has checked exceptions, where you actually have to write code to catch the exception and explicitly handle it somehow. Or it has what's called unchecked or runtime exceptions. And those don't have to be explicitly tested for. if they're raised, if they're thrown, then they'll be propagated, but you don't have to put code to check for them. Most people today consider checked exceptions to be a botch. And so there's a push towards runtime exceptions or unchecked exceptions for almost everything. And you'll see that when we talk about streams. Sadly, Java threads are from the early days of Java. And so as a result, we don't have the cooler features that we do now. OK, this is an example of something called an embarrassingly parallel program. What the heck does it mean to be embarrassingly parallel? Well, what that means is that it's like the phrase, you may have heard the phrase, an embarrassment of riches, which means you have so much of something, it's embarrassing, right? So maybe Bill Gates has an embarrassment of riches, or Mark Zuckerberg has an embarrassment of riches. What it means in this context is that there are no data dependencies between threads. So each thread can run independently, and the computations that they perform never conflict or interfere with each other. So as a result, you can run them very efficiently on multiple cores. Any questions about that? It's a funny phrase, especially if you're not a native English speaker. You're like, embarrassingly parallel. Why would you be embarrassed about that? Well, it just means you have a lot of parallelism. So there's a couple features we're going to look at here. This is the overall design of the program. We have this thing called thread join test with a main program and our main method. And it creates an instance of something called search one-shot thread join that does a bunch of things. And we'll take a look at those things. So one of the things we can do here is we can go ahead and make ourselves a list of worker threads. Because remember, we're going to have them all running in parallel. And so searching for phrases in the complete works of William Shakespeare, or whatever. And we want to be able to do this in a clean way. So down here, we're going to call a factory method called make worker threads. And we'll look at that in a second. We're going to pass in a method reference to the computation we want to run in that thread. And after we do that for n worker threads, where n is the degree of parallelism, then we go ahead, as I mentioned before, and we start each thread by calling for each. So this is a nice, clean little way of doing this that doesn't require a loop. By the way, why do we not want loops? What's the problem with loops? Why do I keep trying to get away from loops? If you recall the first assignment, we talked about that. What are loops? What have loops ever done to us, right? Why are loops bad? Anybody want to make a guess? Yeah.
Because they're inherently sequential.
They're definitely inherently sequential. Interestingly enough, for each is sequential too, but that's another story. And if we were to say worker threads.stream.parallel for each, then it would run in parallel. But yes, they're definitely inherently sequential. That's a good answer. Yeah.
Being like off by one a lot of the time?
Yes, the so-called fence post errors. So loops are just one of those things that tend to drive you crazy because if you're not careful, you'll be off by one. How many times, if you write a lot of code that uses traditional for loops in Java or C or C++, you'll sometimes forget whether it's less than max or less than or equal to max, and then you're off by one. Now, obviously, using things like a for each loop makes that problem go away, but we're still at what you were saying where they're inherently sequential. Did you have anything else to add, or was that?
I was just going to say the same thing.
OK.
Loop variables.
Loop variables are error prone. So for each just makes it a little bit more compact as before. Another thing we're going to show is how to pass a method reference to a method that expects a functional interface. So here is make worker threads, right? This is a factory method. Hopefully you remember from the earlier courses you took, like CS251, if you took it here, we talked about different patterns. Factory method, so a method that makes something is a factory method. So make worker thread is a factory method, and notice what we're doing here is we're passing it a function. And so here's the method reference, and here's the method. And as you can see, this method takes a string and returns a void. And so we're able to process input in as the method reference to the make worker threads factory. Now, why is that a win, right? What is the benefit of passing this thing in as a function, passing a method reference to a functional interface? Why is that good? Why is that helpful? We can have multiple threads doing different things, and we can easily change what those things are, right? So we haven't nothing's hard coded. We make that as a parameter you can pass in. So in this case, we're using this process input method, but we could have something else, and they can still reuse the factory method and easily parameterize its behavior. Here's an example of using a function lambda to create the runnable that's processed by a thread. So if we were to kind of peek inside the implementation of make worker threads, you'd see that we go ahead and we make ourselves an array. It's an array list of worker threads. And then for each element in our input list here is like, let's say each input string is a work of Shakespeare, right? So we have like 37 strings or whatever, one for each play that he wrote. For each input string, we're going to go ahead and create a new thread by calling, create a new thread whose runnable parameter will be whatever we passed in as the function to the factory make worker threads. So down here, we're making a new thread and giving it this runnable, because that's what gets returned here. We're going to give it this runnable to run. And, we're calling task apply, which is going to give us the computation that's going to go in here to run. And when we're all done, we're going to have an initialized list of worker threads, each of which has been given a task to carry out. So that's using a function interface to apply to the input, and that's what's going to get computed in each thread. And then the final thing, once we make ourselves this list of worker threads, we start them all up, then they're off and running, and they're doing their parallel searching and so on. And then the main thread of control is simply going to wait for all the threads to finish. So it's going to join with them. And that's what's often known as barrier synchronization. So barrier synchronization simply means there's a barrier and you can't proceed until all the other things have stopped. A good example of barrier synchronization might be something like when a store opens in the morning, nobody can enter the store until it's open, right? So there's a barrier. Even if there's people queued up outside waiting to get in, they have to wait till the doors open. So that's called an entry barrier. Likewise, there's also the concept of an exit barrier. This is an example of an exit barrier. So when a store closes at night, then you can't, the last employee can't leave until all the other customers have left, right? So that's an exit barrier. Once the last customer goes away, then the employee can turn off the lights and lock the door and shut it down. No other Java synchronization mechanisms are needed in this simple example. And the reason why they're not needed is because it's embarrassingly parallel. So as a consequence, there's no other dependencies other than just waiting for things to be done. If it was not embarrassingly parallel, we would need other synchronization mechanisms in order to protect the data to make sure it wasn't corrupted from simultaneous access. That, of course, is the challenging part of concurrency. All right, so that's a simple example, nothing deeply profound, but it just shows that we can use those Java 8 features with threads. So there's another version which you could look at that used Java 7 to do this stuff. Here's a little snippet of that code. You can go look at the rest of the code if you want to see more details. Notice how back in the original example, we used the classic for loop for I equals 0, I less than the number of strings to search. We make ourselves a new task, passing in value of I, and so on. Here's the make task method. We make a new runnable using the somewhat verbose inner class syntax, which has new runnable, public void run, blah, blah, blah. So that's kind of what it looked like before. And this is more hard-coded than what we had before. So this version, because of the way it's programmed using explicit loops and using inner classes and hard-coding things and so on, just turns out to be more tedious and error-prone to program. It's not wrong, it's just more work, right? So in contrast, the Java 8 version is more concise and extensible. So basically, we pass in the parameter. We are using cleaner ways of creating things. We're not using loops, for example. And so it's just ever so much cleaner. However, those are actually fairly microscopic improvements in the grand scheme of things. So there's still problems with the Java 8 version. In particular, there's so-called accidental complexities. Accidental complexities are complexities that arise from limitations with the tools and the techniques and methods that we use to program. In other words, we don't have to do it this way. It's just limitations with the tools we're using or the languages. So there's still some problems with the features that we used in the Java 8 version. So for one thing, we had to manually create and join threads. So even though it was a little cleaner by being able to reuse these Java 8 declarative features like for each, which got rid of the off by one fence post loop errors we talked about, we still end up having to start the threads ourselves. We have to join with the threads ourselves. So that's extra work, and you might forget to do something, and your program might be ever so much more difficult to debug. A deeper problem, more of a design problem, is because of the way we wrote this thing, we've hard-coded the concurrency model. There's only one concurrency model, and that concurrency model is thread per input. So the number of threads is a function of the number of input strings, which might or might not be good. Maybe it works well, maybe it doesn't, but it's hard-coded. So if you want to change it, there's a lot of work involved. So if you want to make any changes to the program, if you want to modify the concurrency model, for example, you've got to get in there, with your chainsaw or your X-Acto knife or your jackhammer or whatnot, and make a lot of modifications to the code. And the reason why that's the case, and this is very typical, is because the code is insufficiently declarative. It was imperative. We were telling the computer what to do, not saying what we wanted to have done, and let the software infrastructure, the class libraries and virtual machine, figure out how to actually do it. So that's the problem. Now, solving all this stuff is going to require more than just the foundational Java 8 features. So that's what we're going to be covering shortly: parallel streams and completable futures. OK, so that's the end of the discussion about the foundational